limits some more. That's what I want to do. One or two more examples, maybe just one, on the topic of the definition of the limit of a function, the epsilon and delta definition, right? We did a bunch of examples last time and the time before. Is it all right? Yeah, that just says the epsilon and delta definition. Let's do one more example, which is a little more complicated. So here is one last time. Limit as x approaches 2 of x cubed is, everybody knows, 8. All right. Let's see if we can prove this using the epsilon and delta definition. You will see where it gets a little complicated. We can just start off in the usual way. So I'm going to try and write a little proof of this. I always say let epsilon greater than 0 be given. We'll find delta, welcome back, greater than 0, such that. So the setup is 0 less than x minus 2 less than delta implies x cubed minus 8 less than epsilon. We've done these enough. I hope you remember the format. Yeah, sit over here. I can't figure out how to get it over there. I don't know why. Hello to the folks back home. I hope you can see and hear me. I noticed I left my Zoom on in my office with my laptop, just looking. That's my wall there. We'll see if someone tries to steal my hipster poster there. Okay, the typical procedure at this point in the problem is I write a blue bracket here. We start with this thing, x cubed minus 8, and we somehow try to extract from that what in this example would be x minus 2, right? Sometimes it happens sort of by magic, by just like doing some weird simplifications, and then it just comes out sort of automatically. Although here, I don't know so much about this one. How are you going to pull x minus 2 out of there? Anybody have any bright ideas? This is, yeah.
Isn't there a way to factor perfect cubes?
Yeah, do you know something about some kind of formula for the difference of two perfect cubes? There is such a formula. So the basic lesson from this particular example is sometimes you got to just use some random facts that you know. And that's an unfortunate situation because I don't like to just pull random facts out of nowhere, but sometimes it's necessary. If you're trying to do stuff involving, say, sines and cosines, you may have to use some of those weird, obscure trig formulas, right? But anyway, there is a formula for the difference of cubes here. Everybody knows the difference of squares formula. A squared minus b squared is a plus b times a minus b. Anybody actually know this one? This is not a formula that I typically know, so I looked this up. Here it is. I still don't know it. I'm looking at my paper here. A minus b times a squared plus ab plus b squared. All right. It's true. This is a true fact about the difference of cubes. So now that you know that, then you can try to use that formula down here. Now, in this example, in my case, the a will be x, because what I have is x cubed minus 8, right? So in my case, the a will be x, the b will be 2. And what do we get down here? It's inside absolute values, but first I see a minus b, which would be x minus 2. I like that. That's what I wanted. And then some other leftover stuff. A squared plus ab plus b squared. In my case, that would be a squared is x squared. AB would be 2x. B squared would be 4. All right? So I have used my special random fact. Given that you have to just pull these individual facts out of nowhere, it should occur to you that perhaps this proving limits of various functions might be a hard thing to do in general. Like every different example function, you're going to have to pull out a different random fact in order to do this weird, in this case, a factoring trick. It's true. Actually, there are better ways to do it, better than using this limit, this definition as we're doing it here. When we're going to talk about it. Anyway, we did that. Let's separate out. Just because I like to see this x minus 2 part is kind of what I like. This other stuff over here, I don't really like. Because, I mean, maybe we could have hoped that this would further factor into another x minus 2 maybe. That would have been nice. But actually, this doesn't factor anymore. So we're going to have to just leave it like it is. At this point, I'm going to do a similar trick to what we were doing in the examples last time, where you say something like, well, if delta is like less than 1 or something, then x has to be within a certain range, and this other stuff has to be in a certain range too. To sort of get ourselves warmed up for that, or in preparation for that, I'm going to use the triangle inequality here. So remember the triangle inequality? In general, it says, you know, if I have absolute value x plus y is less than or equal to absolute value x plus absolute value y. All right? I'm going to do that on this big part. I leave the x minus 2 is already what I want, so I'm going to leave that like it is. But this part over here, I'm going to replace by absolute value x plus 2 absolute value x plus absolute value 4, which is 4. All right? So I split up the absolute value of the sum of things into the sum of the absolute values, and I factored out the 2 from the middle one. And then the 4 at the end, absolute value 4 is the same as 4. So it's like that. All right? And I put less than or equal in that step because I used the triangle inequality, which is an inequality. All right? And now I would like to say, can I make this one less than some particular constant? We have to be specific about what constant precisely is that less than, but I'm going to do the same old trick. I'm going to say something like, if delta is less than 1, then remember x is within delta of 2. That's what this stuff up here says. Distance from x to 2 is less than delta. So if if delta is less than 1, that means I have 2 here, up to 3, down to 1. X is in this range, right? X is in there. And so can you give me an upper bound on x? So I'm going to continue this thing. I leave x minus 2 like it is because I like the way that is. But what can you do with absolute value x? I want to say that's less than or equal to some specific number. What do you say? I'm going to replace these absolute value x's with specific numbers. What do you think? If x is in there, I'm going to leave the plus 4. Yeah. Yeah, x is less than 3. If x is in this range over here, then the absolute value of x is going to be less than 3. So I can replace all those absolute value x's with 3's. So I put a 3 squared plus 2 times 3 plus 4. All right? But now that I mean, I can just add all those numbers up together, right? This is absolute value x minus 2 times, what is that? 9 plus 6 plus 4, 19. Do you expect the number 19 when you came to class today? I don't know. But anyway, this thing is less than x minus 2 and absolute value times 19. And now we can proceed like the examples from last time. Now we say we want absolute value x minus 2 times 19 to be less than epsilon. So you divide the 19. You get epsilon over 19 is basically what you want the delta to be. All right. This is all that's the bulk of the work. You know, when you write the proof, that's really technically sort of the sidebar. But now I'm going to finish the proof. So I say let delta be, remember in this one, I want delta basically to be epsilon over 19, but we also need to make sure that delta is less than 1. So I say delta be the minimum of 1 and epsilon over 19. And then we write all of this stuff. So then if 0 less than x minus 2 less than delta, we have, I begin with x cubed minus 8, all right? And first of all, x cubed minus 8 is equal to x minus 2 times x squared plus 2x plus 4. That was the random fact about how you can factor a difference of cubes. And then we said there was a bunch of inequalities. Eventually we worked this down to x minus 2 times 19, right? But then if x minus 2 is less than delta, and delta is less than or equal to epsilon over 19, I can say this is epsilon over 19 times 19, which is epsilon as desired. All right. So this one is like the examples we did last time, although it requires a few extra tricks on the inside there. Any questions about all of that? You're going to have a chance to do some more of these on the homework for next week. We do have homework due today, although it's a pretty short assignment. Sorry about that. I'm sure you don't mind. All right, any thoughts about this example? This is the last specific example of these limits that I want to do. What I want to do next is to talk about another, an alternative formulation of the definition of a limit, which is more convenient for certain purposes. So our book calls this, well, I'll write it as a theorem. It is called the Sequential Criterion for limits. Actually they say for functional limits, meaning limits of a function. It turns out limits of a function, you can rephrase the definition. Instead of using epsilons and deltas, you can rephrase it in terms of limits of sequences, which actually isn't much better on the face of it, because the limit of a sequence avoids the epsilons and deltas, but you still have the epsilon and the big N, which is not all that much different. But anyway, you'll see why this is actually extremely useful. I'm going to write it as a theorem. We're not really going to do the proof, but I'll try to indicate sort of on some pictures why you should believe it. But it says the limit of the function equals L. This left side, that is indicating really the epsilon delta thing. That is true if and only if some other stuff is true, which involves sequences. Here it is. It says for any sequence xn approaching C. So if you take any sequence of points that converges to C with xn not equal C for all n, that's a little technicality. That little thing is not really going to be very important, but it should technically be in there. For any sequence xn which approaches C, we have f of xn. Of course, this is another sequence. You start with a sequence approaching C, you plug all those values into your function, and the f of the sequence approaches L, all right? So to say that the function approaches L is the same as saying for any sequence which approaches the value C, the function values approach L. So, like I said, I don't want to do a proof of this, but I'm just going to try and indicate on a picture what each of these things mean on a picture. So this one means, if I were to draw this on a picture, it'd be something like here's my function, here's a particular point, the x value is C, the y value is L, and what the statement of the limit means, it means like if you have a small neighborhood over here, which is like the epsilon neighborhood around L, which we write as the epsilon of L, if no matter how small you choose the epsilon over there on the y-axis, there is some delta on the x-axis, this thing down here, v delta of x, such that whenever x is in here, then you put those sort of on the picture. and the y values, those y values end up in here. Whenever x is in this set, f of x, the y value, is in here, this set over there, all right? That's what this is the idea behind the epsilon and delta definition. If the x's are really close to c, then the y values would be really close to L, all right? Now, what is the other half? Sorry, I didn't keep the whole thing on the picture at the same time. What about this sequence part? What does that mean in terms of a picture? Well, this is a spoiler alert. It's going to be basically the same picture. That's the point of this, is that these two concepts are saying the same thing. But it's slightly different because this picture is about sequences. So in this case, you have your point C down here. And you know, on the graph, it has its value up here, which is L. If I were to draw the picture in terms of sequences, it says if I have a sequence xn approaching C, so that would be a sequence like this, whose values, which converges to C. It says when I look at the sequence of y values, that is, I sort of check out all of these y values along the curve, and then just look at them just as if they were y values, they approach the L, all right? So what this one means is, I would say when the n is large enough, sorry, what does it mean to approach the L? It means that for any neighborhood over here, v epsilon of L, the y values are inside that neighborhood. That's the neighborhood definition of what it means for a sequence to converge. So what this says is when n is large enough, f of xn is in here. Right? This is the definition of, this is what it means to say that f of xn approaches L, right? What's the difference between these two pictures? There isn't really much difference between these two pictures. The point of the theorem is to say that these two concepts are saying the same thing. I mean, one difference is the picture on the left involves a little neighborhood over here, a little neighborhood down here, which you don't really see over here, but over here you have this assumption that xn approaches C. And what that means is that no matter what little neighborhood you choose here, the xn's eventually go inside that neighborhood. So really, they are saying the same thing. I hope that you'll be satisfied with this little two pictures rather than going through the detailed proof. You can read the proof in the book. It's not so inspiring. It's just saying these two ideas are the same. All right. So what's the point of this? In our remaining 30 minutes or so, I want to talk about two big consequences. And I'm not sure we'll get to the second one, but two big consequences of viewing. The whole point of this is that you can view this limit of a function in terms of sequences, right? You can view the limit of the function as x approaches C in terms of considering sequences of values that are converging to C. Sequences of x's that are converging to C, and then looking at the corresponding sequence of f of x's. Two big consequences. Okay, the first one is algebraic limit rules. Remember, when we talked about sequences a very long time ago, we had certain rules about those sequences, and we went through several proofs of several different rules, but I hope you remember something like if an converges to A and bn converges to B, then an plus bn converges to A plus B, right? This was one of the algebraic rules for limits of a sequence. But if you believe this theorem up here, it says limits of a function are really equivalent to some other limit of a sequence, right? Whenever you have a limit of a function exists, whatever its properties are must match up with the properties of the limits of corresponding sequences. And so, for free, we get, I'll say this automatically means that if you have something like limit as x goes to C of if lim x goes to c f of x equal L and lim x goes to c g of x equals M, then lim x goes to c of f of x plus g of x equals L plus M, right? You can prove this directly using the epsilons and deltas, but you can also say, well, whatever this limit is, it must be the same as the limit of some sequences, but those sequences, they add up using the old limit, algebraic limit rule for sequences, all right? So we get all of these algebraic limit rules for functions for free based on the ones which we already proved for sequences. So I'm going to write them all down. We don't need to prove them because, like I said, they come for free because we already know this, the corresponding statements are true for sequences. So our book calls this the algebraic limit theorem. Algebraic refers to like adding and multiplying things. So it says it's basically what I just said, although there's other ones also. So let lim x goes to c f of x equal L, and lim x goes to c g of x equal M. Then we get, I'm going to write down 4 algebraic limit rules. Number 1 is, these are just the same. If you look back in your notes like a month ago, you will see the same rules for sequences. Lim x goes to c of k f of x equals KL for any real number k. So this one says if you multiply a limit, if you multiply a function by a constant, the limit of that function is a constant times whatever the limit is. The same thing is true for sequences, and so it automatically is true for functions too. All right, next one. That rule, by the way, is why you can factor a constant out of a derivative, because derivative is a certain kind of limit. You can pull constants out of the limit. The next one is the one I already wrote before about adding. The limit of f of x plus g of x of two functions is the same as adding their two limits, L plus M, all right? And this is why the derivative of a sum of things is the sum of the derivatives, because it all works out nice with the limits in the definition of a derivative. Okay, you can also do this with multiplying, which is not really true for derivatives, because when you're multiplying derivatives, you have to use the product rule. But anyway, when you are multiplying ordinary functions, you just get L times M. And then the fourth one is about quotients. So lim x goes to c, f of x over g of x, this equals L divided by M, provided M is not 0. And if M is 0, then you've got problems. All right, so these are the algebraic limit rules. I want to just very quickly demonstrate these are really quite useful, although we're not often going to use them, I think, just like very, very specifically. But here's an example. I can show you that limit as x goes to 2 of x to the 4 equals 16. All right, here's an example. Remember at the beginning we had x cubed equaling 8. Now here I have x to the 4 equals 16. If you tried to do the proof the way that I did, the one for x cubed, you have to use some other random fact about fourth powers, which I don't know off the top of my head. Although I actually get a little lucky because here they are fourth powers, but they're also squares. But if you try to do the fifth power, say, you wouldn't be able to do that. Anyway, we can use the rules. Right? Check it out. Lim x goes to 2 of x to the 4 is the same as lim x goes to 2 of x times x times x times x. Right? I write it as a product, and then I use rule number 3. It says if you have a product of a bunch of things, you can just multiply the limits of those things. So this is the same as lim x goes to 2 of x times lim x goes to 2 of x. There's going to be 4 of these, right? And then what are each of those? What is the limit as x goes to 2 of x? It is 2 times 2 times 2 times 2. Now that, I don't know if we prove that as a theorem, but you could easily prove that with the epsilons and deltas. You let epsilon equal delta and everything works out perfectly fine. So and anyway, that's 16, right? So you can do proofs like this without using any special tricks. So that special trick I did for the cube difference of cubes, it worked, but that is really kind of the hard way to do that problem. It's much easier to break it up like this. You don't need any random facts about anything. All right? Any thoughts about that? When you can, use the limit rules rather than the epsilons and deltas. That's the moral of that story. Okay? I said we had 2 things. We got plenty of time. Let's do the second big consequence of the sequence definitions. So, another consequence of the sequential criterion is a fairly manageable way to show when a limit does not exist or when a limit does not equal something. So I'll say a nice test to show that a limit does not exist. For example, let's see if we can show lim x goes to 3 of 1 over x minus 3. This does not exist. It's true. It's a fact. What I mean by limit does not exist, very specifically, what I mean is, i.e., no L exists with lim x goes to 3, 1 over x minus 3 equal L, right? That's what I mean when I say the limit does not exist. There's no possible value that you could put there which would make the limit equal L. But this, as written, this is very hard to show using the epsilon and delta definition. I don't know about very hard, but it's not something that, you have to go through that epsilon and delta definition, which is very complicated and strange, and do the negation of all of that. Turns for all epsilon into exists epsilon, turns the exists delta into a for all delta, and then does weird things with the rest of it. You don't really want to try and do that. There's a better way to do it in terms of the sequences, all right? So it does mean that no L exists that satisfies that business. Anyway, it's easier to translate the whole thing into sequences. All right? Remember, the limit of a function existing is the same as saying the limit exists when you take all sequences of x's which approach c, and the limits of the f of x's approach L. All right? So I'm going to say it this way. If you say lim x goes to c f of x does not equal L, this is the same as saying, so I'm going to write the opposite of the big theorem that I wrote at the beginning. Remember, the limit equals L means for every sequence xn approaching c, the values f of xn approach L. So the limit does not equal L is equivalent to saying there exists a sequence xn approaching c. Technically, xn is not allowed to equal c for any n. Such that f of xn does not converge to L. All right? That's the opposite of what I said before. What I said before was for all sequences xn converging to C, then f of xn converges to L. This is the negation of that. There is some sequence which converges to C, but the f of xn's do not converge to L. All right? Let's see if we can do an example, very specific example. Oh, okay, sorry, I want to revisit that example right there, but let me just say, another version of this, so what I just wrote is that, is what it means when the limit does not equal L. What about the limit does not exist at all? Limit x goes to c, f of x does not exist at all. Well, to write that in terms of sequences, I'm going to write the same thing, but instead of f of xn does not converge to L, I'm just going to say does not converge at all, right? So this will say, exists a sequence, xn approaching c, with xn not equal c for all n, such that f of xn diverges. All right. This is going to be the easiest way to demonstrate that a function's limit does not exist. You find a sequence of x values such that when you plug them into the function, it makes a sequence which diverges. All right. Let's try that particular example that I said before. Lim x goes to 3. 1 over x minus 3 does not exist. All right. I hope you all agree, right? 1 over x minus 3 would look something like this. Like this, right? That's what the graph of that would look like. Anyway, what our job is, we have to find some sequence according to this business up here, right? We will find a sequence xn approaching c, which in this case is the number 3, with the sequence f of xn as the sequence diverges. Can we do that? Can anybody think of a sequence xn which approaches 3? Like on the picture, I would suggest maybe a sequence which approaches 3, say from the right side. Then the y values, when I plot them on the function, they will go up like crazy, won't they? And so they will diverge. That's the idea. Can we think of an appropriate sequence? You have to be specific about this. There are many possible answers, but what do you think? I want a sequence which approaches 3. Once you do a few examples like this, you will have some more intuition about this. What do you think? You don't have to be too fancy, yeah?
3 plus 1 over n.
Yeah, how about 3 plus 1 over n? This is a go-to kind of thing. If you want a sequence which converges to a particular number, think about 1 over n, which goes to 0, and then just like add something to it. So 3 plus 1 over n is a great idea. All right, we need to verify that f of xn diverges. This is going to look a little weird, but we can handle it. Then what is f of xn? You plug 3 plus 1 over n into your function, which in this example, I suppose I didn't ever write it as a function, but the function I'm talking about, of course, is 1 over x minus 3, right? So what does it look like when I plug in xn to that formula? I plug 3 plus 1 over n into f of x. It looks like 1 over 3 plus 1 over n minus 3, right? I used this formula here, and I plugged, instead of x, I used 3 plus 1 over n. I need to show that this diverges. Can we simplify anything here? Well, you bet we can. The 3's will cancel down there, and then I have 1 over n, which is n. And would you say that this diverges? Yeah, it does. So f of xn as a sequence is just n. It's just 1, 2, 3, right? Which diverges. That's it. All right. So when you're trying to show that a limit does not exist, you got to find a particular sequence and then demonstrate that when you plug that sequence into the function, the limit of that sequence does not exist, which is typically going to be a lot easier than dealing with the epsilons and deltas directly. All right? Great. Let's try another sort of wilder example than that. Are there any questions about that? In this example, you could have basically used any sequence which converges to 3. You could have used 3 minus 1rn if you wanted to. Then actually, if you worked out the details, that would be this sequence on that side, and you would have gotten negative n in this position right here. But still diverges. Okay, now this one diverged because like the values went up to infinity. We know it's possible to diverge because the values, maybe they oscillate between two different numbers. It doesn't have to be that they go out to infinity. Let's try one like this. Here's a very weird example of a function. One of my favorite functions. F of x equals sine of 1 over x. I don't know if you ever considered this function. The graph of this looks kind of cute if you can graph this on your calculator. Everybody knows, sine of x, this is not what the function I'm talking about right now, but sine of x goes up and down like that, right? Back and forth. What is sine of 1 over x going to do? Well, it's still, first of all, it's still the sine of something, and so all the values will be stuck between 1 and minus 1, because the sine of anything is values always between 1 and minus 1. But when you get close to 0 here, when the x gets close to 0, this 1 over x will go to infinity sort of increasingly quickly. As x approaches 0, this number will increase like crazy. What that means is this kind of oscillation, as x approaches 0, the frequency of the oscillation will become extremely fast. So I'm going to get rid of this. That's not what I'm talking about here. What it's going to look like is, I'll draw it in red. It doesn't look so interesting out here, but as it gets close to 0, the oscillation in the sine just gets super rapid and sort of, it oscillates infinitely quickly as it approaches the origin. And same on the other side. You can graph this on your calculator. You'll see a picture that looks something like that. It's kind of cute. You get something even cuter, by the way. I don't know if you like cute pictures. X times sine of 1 over x. I can remember. This memory just popped into my memory. When I was a senior in high school, I remember sitting in my math class, and this kid was like sitting, in the aisle next to me. He was like, "Hey, check this out. I got something to show you." And I was like, "Whoa, what is this kid going to show me?" He showed me his calculator, which had a graph of this function, x times sine of 1 over x, which he thought was the awesomest thing in the world. It's the same as that picture there, but all the values are multiplied by x. So instead of it being between 1 and minus 1, they're between x and minus x. So it ends up sort of being the same picture, but it's stuck inside this thing, and it goes like that, sort of. Which this guy thought was pretty awesome. It's kind of awesome, I guess. It doesn't actually do that right there. That's not part of it. Okay, so anyway, what can we say about this? Now, what would you say lim x goes to 0, sine of 1 over x is? This is actually a function that a typical calculus student looking at this might be kind of confused by, or something. Like, this is an example where your ordinary conception of what the limit means doesn't really apply to this function. But I think even a know-nothing calculus student, or even a kid like myself in high school, would be forced to decide that I guess the limit doesn't exist, because like the limit certainly isn't equal to 3 or whatever. Like, it's not equal to 0, because this function oscillates infinitely often. So this limit does not exist. Can we demonstrate that? It's not so hard if you're using sequences here. So we need to choose a sequence, right? xn, which goes to 0, because that's the value of c in this case. It's the value the x's are approaching, where f of xn diverges, does not converge. Now, in this case, f of xn will not go out to infinity because you can tell by looking at the graph, these values do not go to infinity, but the divergence occurs because the values are jumping back and forth so in such a crazy way. They don't converge to anything. All right, now we got to be a little cute about choosing the sequence in this example. If you decided, so this is not what I'm about to write is kind of a bad idea, but you might be tempted to just say, well, I'll use 1 over n because that goes to 0. I want a sequence which converges to 0. But then we get f of xn is sine of 1 over n, and that is a little too crazy for me to get a handle on. Sine of 1 over n, this as a sequence would be sine of 1, sine of a half, sine of a third. Actually, with my superior calculus knowledge, I don't know any of those values, right? Sine of 1 is just some weird number, and same with sine of a half or a third. I don't know what any of that is. I only know sine of something involving pi, right?
Would you get sine of n, not sine of 1 over n?
Sine of n, yeah, thanks. Everything I just said still applies, but yeah, you're right. Sorry about that. I forgot the extra 1 over. I get sine of n, right? This is not a nice sequence, though. Sine of 1, sine of 2, sine of 3. Those are all just sort of random numbers, which I don't like. Would anybody like to suggest a better idea here? Perhaps you got to cook up this sequence so that at this point it becomes something that you know how to maybe evaluate the answers of or something. Choose the original sequence so that once you plug it in the function, you get something that makes a little bit more sense. What do you think? Yeah?
You like 1 over pi n?
1 over pi n. I like that a lot better. Is that what you were going to say? Yeah. So actually, that's not my final answer, but I'm gonna write that for now. 1 over pi n, right? So what this looks like is, if I use xn equals 1 over pi n, then f of xn. So I'm gonna modify that slightly because you'll see in a moment this doesn't quite work. But what do you get then? You get sine of pi n, right? Okay. Now I wanted to choose this so that when I plug it into the f, the sequence diverges. Does that diverge, sine of pi n? Actually, it doesn't. What are those values? That would be sine of pi, sine of 2 pi, sine of 3 pi. Any calculus masters out there? Trigonometry masters? What are those? Sine pi,
There's 0 or 1, I don't know what.
sine 2 pi. Actually, it's even better than that. These ones are all 0, right? The graph of sine is this. Yeah, so these are all 0. So good idea with the sequence, but it turns out this one doesn't diverge just because we picked the values are kind of too good. Wouldn't it be better if some of them were 1s and minus 1s, something like that? Like then this thing would actually not converge. The problem here is we have to choose a sequence in such a way that f of xn diverges, but that one is always 0. Yeah.
Negative 1 to the n. Pi times pi, 1 over.
Pi times minus 1 to the n. So you want to put alternation of the signs in here,
Yeah.
or you mean
Yeah.
minus 1 to the n out front? I'm not sure that's going to work.
Later,
Yeah, you get like minus signs on the inside of every other one of those, but actually those won't really matter because they're still going to be 0 anyway. Any other ideas? These are good ideas. You just have to arrive at the proper thing. I would like to make it so that instead of getting 0s here, I get some 1s and minus 1s also. That would involve taking these values, not just the multiples of pi, but those other ones. Yeah?
1 over pi over 2.
Yes. So you want, basically, I messed that up by putting that. You want pi over 2 instead of pi. What? Not pi over n. Pi over 2 instead of pi. Then everything works out great. Okay, so now when you put a pi over 2 there, I got a pi over 2 down here. And then this stuff over here is, well, it's sine of pi over 2, then sine of pi, then sine of 3 pi over 2, then sine of 2 pi. And this is 1, 0, minus 1, 0, 1, 0, minus 1, 0, etc. And that, my friends, does not converge, right? This diverges. How do you know that doesn't converge? Well, it's bounded, but I can find sequences which converge to 2 different values. This is something that we used to talk about quite a bit more, but this diverges. If you really wanted to demonstrate very specifically why, it has subsequences which converge to different values. For instance, it has this as one subsequence because it's possible to just choose those zeros going out forever. And then it also has, you could make this as a subsequence because it is possible to choose just the ones going on forever. Right? This one converges to 0, this one converges to 1. And so that means the original sequence cannot converge. All right, and I think that'll do. We're going to do a couple more examples like that next time.